Welcome to lesson number 6 of our series in real analysis, and in this video we would be talking a little bit about the rules of algebra of sets, complement of sets, and specifically we are going to look into De Morgan's law and how we can prove De Morgan's law using simple basic examples. We are also going to look into a glimpse into the life of De Morgan, and we will sum up everything nice and in an easy manner. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to lesson 6 on real analysis. We are still continuing with algebra and the operation on sets. So when we start with the algebra of sets, we need to find out the rules. Just a note to the viewers that we are not going to prove these rules. However, there's a way of proving this rule which I would do if you really want, and put up your comments in another video. So the first rule law which comes up is called the idempotent laws, and it's quite simple. Intersection and union of any set with itself revert the same. So a union of A is A and intersection of A also leads to A. The identity law, which is quite simple. For any set A is the union of phi equals to A, and A intersection with U results to A. I will just like to tell you that U is basically here the universal set. Commutative laws, very simple. For any sets, if you take A and B, then A union of B obviously would be equal to B union of A, and A intersection of B will be equal to A intersection of B. Okay, the associative laws which are taken with three sets A, B and C are this one. You can take a pause and just note it down. A union of B equals to union of C, which is A union of B union of C is equal to A intersection of B equals to intersection of C equals to A intersection of B intersection of C. Distributive laws, again we have to take three sets. A union of B intersection of C equals to A union of B and intersection of A union of C, and it can be also this: A intersection of B union of C will be equal to A intersection of B union of A intersection of C. Now we come to something which we will spend a little bit more time in understanding, because this is very important when we go ahead and learn real analysis. This law will be used in various ways. This is the De Morgan's law. So for any sets A and B, we can say A union of B in a complement is equal to complement of A intersection with complement of B equal to A intersection of B, or we can say equal to complement of A union of complement of B. Now I've used this strike sign, but we can also write it in this way. So C actually denotes the complement, so we will use C so that we can avoid this unnecessary, it might cause any confusion. So A union of B complement of A union of B equals to complement of A and intersection of B, whereas A complement of B intersection complement will be equal to union of A and B complement. Okay, so what does De Morgan's law states? Let us find it out what it actually does. So in one way we can say that it says that the complement of the union equals the intersection of the complements, and the complements of the intersection equals the union of the complements. Or in other way we can also mention like this: the negation of a conjunction is the disjunction of the negation. We use this sign which we have learned in earlier, how we used negation, and conjunction is this one, right? Or, and disjunction or conjunction would be and disjunction would be or. So the negation of the conjunction P and Q is equal to the disjunction of the negations, equal to P and Q, right? And we can also say the negation of a disjunction is the conjunction of the negations, and this is how we write. So De Morgan's law can be stated in both the way. One is the complement of union, the complement of intersection, as well as negation and conjunction followed by its signs. So this is the way in which we can write the De Morgan's law, and here C denotes complements. So union equals intersection and intersection equals to union. That is a basic idea. And the distributive law which we just learned can be stated like this. Here you can see A gets distributed in this part and also in this part. So that is how the distribution takes place, and also this one. So this actually covers up our area in understanding De Morgan's law. But in De Morgan's law, we have seen there are two things which we are not yet learned, which we will quickly do in this video. One is the complement of set, another is the difference of set. So complement of set is basically the set that includes all the elements of the universal set that are not present in the given set. Let me give you a quick example. Let us say A is a set of all coins, which is a subset of a universal set that contains all the coins and notes. So if A is a set of coins which is a subset, and there is another universal set that contains all coins and notes and other, so the complement of set A is a set of notes. Obviously, why? Because it does not include coins. So we can tell that complement of a set is another set that contains those elements which are missing or not found in the set. Mathematically, it is written as this. This is a pictorial description which shows the green area complement of set. So the complement of A, which is given as A with C on the top, or A with a hash sign or strike sign, this is everything else, right? Okay, so complement of set can also be defined as U, which is the universal set, all the elements. Then A is written as this, or it can be written as this in a set builder notation. We can take up an example. For example, if we take a set S, which consists of all the prime numbers up to 17, then S would be 2, 3, 5, 7, 11, so on, and A would be 2, 3, 5, so on. So we do a difference, U minus A equals to complement of A, and we get this. So this completes our definition and understanding of what is a complement of set. And this, as I have noted in red box, this is the difference of sets of two sets. And now we are going to learn how we can calculate the difference of sets. So the difference of set is simple. The subtraction, that is A minus B, which is mathematically written in set builders notation as this. So this is a picture. As you see, X equals to A, B, C, D, E, Y equals to A, B, S, R, T. Then the difference of X minus Y would be C, D, E. That means we have taken the elements or objects of A, X, which are not in Y, right? So not in Y means obviously A, B is there, C, D is not there, so we have taken that. Now one thing is equally important, that is X minus Y is not equals to Y minus X, and this is what it shows. If Y equals to AB SRT and X equals to AB CDE, then Y minus X would be the elements which are not included. So what are the elements? S, R and T are not included in X. So we will not take AB because this is included. We will take S, R and T. So this actually shows a very important idea. When we are taking a difference of sets, X minus Y is not equal to Y minus X, and this actually shows the difference. X minus Y is CDE and Y minus X equal to SRT. So the difference of sets now we can summarize in a pictorial description. This is the union, this is shows the intersection, and this shows A minus B, the difference. Now that we have understood what is the difference of set and complement of set, it is right time that we should go in understanding De Morgan's law a little bit more. But before that, a quick idea about who was Augustus De Morgan. You will be surprised to find that Augustus De Morgan was born in Indian Madras on June 27, 1806. His father, Colonel De Morgan, was working here for East India Company. When De Morgan was 7 months old, there was a Sepoy mutiny in India, and he moved to England, educated in Trinity College, London, and he became a professor of mathematics at the University College in London. This is actually the most important book which you have wrote, Trigonometry and Double Area. As you can see, Augustus De Morgan of Trinity College, Cambridge, and this is considered as one of the most important work and other pedagogical issues of mathematics teaching at that time. At the age of 21, he was appointed the professor of mathematics at the London University, and he taught two great stalwarts, Charles Babbage and Ada Lovelace, and their teaching and foundations further helped us in understanding and formulating the modern theory and understanding of computers. As we know, Charles Babbage and Ada Lovelace, both of them contributed initially in understanding the basic concepts of computer and computation. this was his wife, Sophia Elizabeth De Morgan. In her book 60 and 10 Reminiscences of the Late Sophia Elizabeth De Morgan, she recounts her childhood days, and this is an excerpt from her writing. In the course of a long life, I have met with many persons whose mental and physical lineaments have remained in my mind as clearly as if they were not of the past. Some of these have been well known to the world of duly commemorated. Others have been comparatively obscure but deserving of remembrance as having contributed to make the world what it is, better than our grandfathers found it, but far from what it ought to be and will be some time hence. This is a quick but a very incomplete idea about Augustus De Morgan and his contribution to set theory and mathematics. However, this gives an idea about who was Augustus De Morgan, and we go ahead and understand now what is De Morgan's law, which we have already seen. Now, De Morgan's law is actually divided in two parts. The type 1 De Morgan's law is something like this. We can write the De Morgan's law again, this one, and we will take the first De Morgan law, which is called type 1. So we'll take an example 1 to 11 numbers, which is in a set, and let us imagine this to be a universal set. Then what we get is x equals to 2, 4, 6, 8 and y equals to 1, 3, 5, 7, 9. The question is that how can we prove the first one, this one? So what we will do is that we will approach on the left hand side and right hand side one by one. So first we get this one, that is the complement. So doing a union of x and y, we get this 2, 4, 6, 8 union of 1, 3, 5, 7. We get this one. Now what we do is that we take the complement of the union, and the notation stands as follows. This one, and then we do the difference which we have just learned. So x union of y complement will be equal to this number minus this number, which will be this number, right? So we will take 10 and 11y because this 10 and 11 is not present in y, and we're doing a union complement. Now we start with the right hand side, which is this one, that is the intersection part. So first we find the complement, which is again this subtracted from the other, and we will take this complement. Then we find the complement of y, which is the y complement, that is this number minus this number, and we get those numbers 2, 4, 6, 8 and 10, and you can verify with the other the earlier part which I have just told, that these numbers are not present in x, so we take the complement in this way. Now x complement intersection of y complement is given by this, which goes by this, and here we prove that x union of y complement equals to x intersection of y complement. Now what we are going to do now is that we will just replace the variables which we have just taken as x and y with a and b. So x will be now equal to a and y will be equal to b, and we get this one. So now we move ahead. So you can just take a note that we have proved the first one, that is union and intersection complement. Now once we move ahead to De Morgan's second law, we will do the same approach. We will start with the left hand side. So we started first with the right hand side, now we are doing with the left hand side. So we will deal with the intersection, and we will take the values and we will put the values. Now here is a note that x union of y will become an empty set, right? That is a phi. So our next set would be to find the complement of the intersection, which is this one, and then we subtract it from the empty set phi, and we get this. So we have already got the intersection. X intersection of y complement is this number. Now we will start with the right hand side. We will do the subtraction, that is the difference, and we get s minus y. Then we will perform the union of the complements, that is the first union complement x with the y complement, and then we do the union, and once we do the union we will get all these numbers, which is equation number 2. Now if you remember, we have already proved this equation number 1, so therefore x complement will be the first set minus the second set, and we get these numbers, and therefore y complement would be again the first set minus the 2, 4, 6, 8, and then we get the y complement. So now that we have got the x complement and y complement, we have proved that equation 1 will be equal to equation 2. So in other words, we can say LHS equals to RHS. So you see the intersection equals to the union, which is the complement, and now again we substitute x equals to a and y equals to b. We get this one. And earlier, if you go back to my video, we have just proved the union and intersection complement. So finally we have proved this one. So the De Morgan's law, I won't say it is a proof, but we can substitute these values in order to prove the De Morgan's law, which is now highlighted on the right hand side with a red box. The question is that a De Morgan's law, can we use it in simple English? Because as I have stated in my earlier videos in proof writing, that whenever you're writing a mathematical proof, it is nothing but using the same simple English in mathematical notations. So if we write something like this, not proposition P or not proposition Q can be replaced in a logical proof with not P and not Q, and this is how you do. Again, not proposition of P and not proposition Q can be replaced in a logical proof like this with not P or not Q, which is written as this. You can take a pause of this screen and you can just write it down, that how this simple English language has been now reflected in terms of I won't say mathematical notation, but in terms of logical syllogism or in terms of logic. We can also use Boolean algebra just to interchange of union and intersection using this. So on the right hand, on the top, this is again a bar which actually denotes the complement. So this is the interchange of union. Now, can we use practical usage of De Morgan's law? Yes, very much. In Boolean logic, it is used, for example, NAND gate, that is not and, NOR gate, not and or, XOR gate, and NAND gate, that is exclusive or a not and negative logic gates. We can also use De Morgan's law for general statements. For example, I don't have a book and I don't have a pen can be written like this. I don't have a book or a pen can be written like this, and I don't have a book and a pen can be written like this. So you see, ultimately what happens is that whatever we are trying to express in terms of English are now either been replaced by mathematical notations or by logical notations. This completes our today's video in understanding a little bit about the life of De Morgan, Augustus De Morgan, how it can be used, complement and difference of sets, and how using trivial numbers we can find out the De Morgan's law, the first and the second De Morgan's law. So we can say also statements like this: I did not eat rice or I did not eat fish, which actually means I did not eat both rice and fish, although I might have eaten one of it. So this statement can be written in this way. Again, a simple English statement, how easily and in a condensed manner we can write using the symbols of logic. So that completes our video. Thank you for watching this. Please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. You can contact me at this email ID, and you can subscribe to my other channel, or you can follow me on my Instagram, Facebook and LinkedIn pages. Thank you very much for watching this video.